This is Learning Assessment Problem E224. The objective of this problem is to reduce this circuit to an equivalent single resistance value R sub t at the terminals. When we look at the circuit, we see that there are no parallel or series combinations of resistors at the moment which can enable us to reduce the complexity of the circuit. So the problem-solving strategy here will be to apply a Y to delta or delta to Y transformation to the resistor network. If we look at an amplified view of the circuit, we've labeled nodes A, B, C, G, and the terminals E and F. If we look for those delta and Y configurations, we see two obvious deltas here in the meshes, and wherever we have three elements connected to a node, we can consider that as a possibility for a Y configuration. So in order to do a circuit reduction, we'll apply one of the transformation processes. Let's choose the upper delta mesh to perform a delta to Y transformation. Here we've redrawn the delta equivalent circuit. We've labeled the R1, R2, and R3 values in that circuit. We've made the bottom delta configuration more rectangular so that we can see what we're going to develop as we proceed to the transformation to the Y circuit. On the Y side of the circuit, we've labeled RA, RB, and RC as the resistors that we'll have to calculate in a moment. We've developed another node in the circuit, node D, as a result of this delta to Y transformation. So let's proceed with establishing the values for the equivalent Y-connected resistors. Here we have again the transformation, the R1, R2, R3 values in the delta circuit, and we want to determine the RA, RB, and RC. We had that node D in there. So RA is given as the product of R1 times R2 divided by the sum of the three resistors in the delta. This is 54. This is 54K times 36K divided by 54 plus 36 plus 18, which is equal to 18K. For RB, it's a similar process, multiplying R2 times R3. And the denominator is the same, and that happens to sum to 108K, and this is equal to 6K. And for RC, we have 18K times 54K divided by the 108K, and that RC value is 9K. So we've developed the values of the three equivalent Y-connected resistors. Now we'll go to that equivalent circuit. R sub A is 18K, RB is 6K, and RC is 9K. And now you can see the benefit of doing this transformation. We've developed some series connected resistor configurations, and then we also have a parallel combination to work with. So we'll determine the values of the series connected resistors as RSC is equal to RC plus 3K, and RSC is equal to 9K plus 3K is equal to 12K. And likewise, RSB is equal to RB plus 18K, or that is equal to 6K plus 18K, and RSB is equal to 24K. So we can label those quantities on this circuit, 12K and 24K, and proceed with the next step in the analysis. We see now that we have a parallel combination of two resistors, 12K and 24K. So we can proceed with the next step in the analysis and say that RP1 is equal to 12K in parallel with 24K, which is equal to 12 times 24 divided by 12 plus 24, and that is equal to 18K. So we can put that value of RP1 in the circuit. RP1 is equal to 18K. Now we have a simple series connection of resistors, and RS2 is equal to the total resistance is equal to the total resistance Now we have a simple series configuration of resistors, and R sub T, now the total resistance between nodes E and F, is equal to 6K plus 18K plus 18K plus 2K. Now we can look at the parallel combination of resistors, and our P1 will equal RSC in parallel with RSB. That is equal to 12K in parallel with 24K. R sub P1 is equal to 8K. We can put that resistor RP1 in the equivalent circuit, 8K, and finally we're ready to calculate the total terminal resistance RT is equal to a series combination of 6K plus 18K plus 8K plus 2K, or R sub T is equal to 34K.